Hello everyone, welcome to MathPrax. I can't help it. I have to create a video that relates to practice problem number 5 about a microcontroller and its flash memory. So today I am going to show you on real hardware how a record can be flashed sequentially without gaps, exactly replicating the number of bytes for each calibration entry in our last practice problem. This is one of the boards I have here at home. This big square black thing is the microcontroller itself, and this can be programmed using this software you see here. There is a red LED indicator that toggles every second, a user button, this blue thing right here, a reset button, the black one, and a connection to the host computer through this ST-Link chip right here for debug and serial communications. I have prepared a quick firmware in order to demonstrate records flashing, as well as looking into the flash memory layout itself and confirm if we have saved the records correctly. Another nice thing to have here is this tiny Python script running on the host computer, which listens to microcontroller serial messages and prints them here on the PowerShell window. Through this, we get real-time feedback on what is going on with user actions. Was the record flashed? What is the starting address? What is the address for the next calibration record? A record can be flashed by pressing the user button while it is running. And the entire flash region allotted for the records can be erased as well by having the user button pressed during the firmware startup. In short, hold it and do a reset. Looking briefly at the firmware, the initialization code is generated by this software. Here you can see how the microcontroller is configured. There is a pin that senses when the user button is pressed. There is a pin that turns the red LED on and off. And there are pins configured for serial communication to the ST-Link chip, so that serial messages from the microcontroller can be received by the Python script and print them here. Here we see the application code. The messages are prepared here on top. So that we can inspect the flash memory contents, this is the expression that points to the starting address. In fact, if I let these lines execute here, and again hit a breakpoint right after, we can already inspect the contents of the flash memory. Looking at the first record, the details here say that this value repeats 128 times. This is the indicator that that address isn't occupied yet. Of course, the succeeding records aren't occupied as well. So what messages does the Python script receive? A welcome message. The starting address of the allotted space for all the records. If the user intended to erase the entire allotted space. The free address where the next record will be flashed. And when flashing a record was performed. These are the user feedback that give us hints about what the device is doing. This is a dummy calibration record. If you think of this microcontroller as a measuring device, then these bytes could be the correction values for the actual device measurements generated during a calibration routine, and that these bytes are received by the microcontroller from an external tool through any of the most commonly used communication interfaces like USB, UART, or even Ethernet connection. For simplicity, this is the only record that will be flashed successively in the memory. Now, once the while loop is entered, the microcontroller toggles the LD3 or the red LED every second and periodically checks if the user button is pressed. And when pressed, flashing one record will be performed, the feedback message will be transmitted, and the address for the next record is prepared. So now, let us see this in action. I will press the user button. Execution halts here. A message is received by the Python script telling the used record address. We can inspect the pointer expression here. And sure enough, the record values are there in the first one. We can inspect deeper and compare the values with the record in RAM. Yes, they are the same. Let the code run. Press the user button again, and again, and again. Now I will reset the microcontroller and let it run freely. Pressing the user button repeatedly, as you can see the messages here. Okay, this is the last used address. How many records exist in the flash now? On the right side here, we can see that A sub 1 is given, as well as the common difference. If we know the ordinality of a record, then we can solve for its location address. On the other hand, if we know what the last used address is, then we can solve for which record it is. So using the last address here, minus A sub 1. Divide that by the common difference, and add 1. There are 15 records existing in the flash memory. Let us inspect. Confirmed. Follow-up question. Which line of code contains the arithmetic progression formula? Feel free to give your answer as a comment. I hope you liked this demonstration. Thank you for watching, and if you found this video helpful, please hit that subscribe button so you don't miss out on my next tutorials. I'll see you in the next one.